This short lecture describes the analysis of the data obtained in the mini-lab exercise called the work energy theorem. This mini-lab exercise is completed on handouts. I'll be referring to those handouts as I walk you through the analysis of the data that is obtained. Okay, before doing so, however, let me briefly go over the theory behind the laboratory exercise. That is the following. Okay, so here is the mini-lab entitled Work Energy Theorem. Here is the theory behind the exercise. Okay, what I'm going to do is I'm going to take my dynamics cart like so, which has a mass m. The mass of the dynamics cart, by the way, is the same for everybody in this exercise. It is 60 grams. 60 grams is equal to 0.06 kilograms. Then I have my string like so tied to the cart, the string that is draped over a pulley here like so off to the side. And then I have an object here, a laboratory weight, that is hanging off to the side. I then have my piece of strip tape like so that is taped to the cart. It is then threaded through the spark timer, which is back here. Okay, and then I release the cart from rest. So as the cart accelerates, it then gains kinetic energy. Net work is being done by the cart. Ultimately, the net work that is being done is supplied essentially by the laboratory weight that is hanging over the side. So we have net work is equal to change in kinetic energy. So on the right-hand side of the expression, we have change in kinetic energy being equal to the final kinetic energy, 1/2 mv squared, minus the initial kinetic energy, which is equal to 0, because ultimately we're assuming that the cart starts from rest. And then on the left-hand side of the expression, we have the net work done. The net work done is equal to the dot product between the net force and the displacement delta R. The net force that's exerted upon the cart, however, is ultimately horizontal in this direction like so. And that's in the same direction as the displacement vector delta R as the cart accelerates across the desk. So because these two vectors point in the same direction, there is a 0-degree angle between them. We then take the dot product between those two vectors and we have the cosine of 0 degrees, which is equal to 1. So then basically what we end up with here on the left-hand side of the expression is force times distance. Like so, and that then equals the right-hand side of the expression, which is now just the final kinetic energy, 1/2 mv squared. Now, of course, from Newton's second law, net force is equal to mass times acceleration. And then the displacement delta R is the same thing as the position x that will ultimately measure on the strip tape itself. This then equals the right-hand side of the expression, which is just the final kinetic energy, 1/2 mv squared. So basically what we'll do in this laboratory exercise is we'll calculate each side of this expression, and then we'll compare the two sides to each other by plotting them against each other. When we do, we should obtain a line where the slope of that line is equal to 1. If we do, this then means that the net work done is equal to the change in kinetic energy. That's the theory behind the exercise. Okay, now the procedure is as follows. Okay, so I set up the situation as described. I refer you to that video that shows the obtaining of data that is necessary for this laboratory exercise. And now we'll go ahead and analyze our tape. So here is our strip tape like so. Okay, as is always the case, there's a little bit of smear at the beginning here. That then corresponds to the time between turning on the timer and letting go of the cart. And then after the cart accelerates across the desk, then the dots get progressively further and further apart. Now, what we are assuming, remember, is that the cart begins at rest. So then therefore we have to choose the first legible dot after the smear as dot 0, because that's as close to the beginning of the tape as we can get. So right here is dot 0. We then choose the first legible dot as dot 0, and then number out 1, 2, 3, 4, and so on, ultimately out to dot 9 as usual. Now in this laboratory exercise, I essentially divide up the data into two data tables. So let's take a look at the first of those two data tables. It is the following. Okay, so we have 4 columns here. We have dot number first of all, which is referred to as N, 0, 1, 2, 3, and so on, up to dot 9. and then the position of the nth dot in terms of meters, where dot 0 is our origin. We'll measure in centimeters, that's perfectly fine. We'll measure to the nearest tenth of a centimeter for the positions as always. However, when we tabulate here, we need to divide by 100 to convert from centimeters to meters. Then in our next column, we have the time at the nth dot in terms of seconds, where we start our clock at dot 0. And then recall that because 60 dots are made per second, the time at the first dot is 1/60th of a second, 2/60ths of a second, and so on up to 9/60ths of a second. And then the last column for the first data table is the calculation of the velocity. The velocity at the nth dot in terms of meters per second, and we'll use the following formula to make that calculation as always. Okay, so recall from previous laboratory exercises that the velocity at the nth dot is calculated in the following manner using this formula. Like so, where delta t is the time interval between successive dots, and that's 1/60th of a second. So recall that the denominator of the expression is always 2/60ths of a second from previous laboratory exercises. And here is the example that I always depict in those laboratory exercises. So for example, let's say that we have to find the velocity at the 6th dot. So then what we do is we take the position of the dot ahead of it, which is dot 7, subtract from that the position of the dot behind it, which is dot 5, and then we just divide by 2/60ths of a second. Recall the shortcut, however, because we're always dividing by 2/60ths of a second, is the same thing as taking the numerator of the expression and then just simply multiplying by 30. Like so. Recall, however, that we cannot use this process to find the velocity at dot 0. However, we are assuming that the velocity at dot 0, remember, is equal to 0. So then therefore, that's why there's a 0 here in that position for the velocity at dot 0 in the data table. However, we of course cannot use the formula for dot 9 because we don't have a dot 10. So then therefore, we put a slash here like so for the velocity at dot 9, as we always do. Then we're going to obtain the acceleration. We'll obtain the acceleration, as we always do in laboratory exercises such as this, by plotting in the first graph velocity as a function of time. So now refer to the first graph in the handout. Okay, so on that piece of graph paper that's provided for you, you then plot velocity at the nth dot in terms of meters per second as a function of time at the nth dot in terms of seconds. So along the horizontal axis here, we'll have 0, 1/60th of a second, 2/60ths of a second, 3/60ths of a second, and so on. And then based upon our velocity calculations for dots 1 through 8, we'll then figure out how to scale the vertical axis. Ultimately, when you plot the points, you'll obtain a line like so. And then, as is always the case, we'll use a ruler to then draw a best fit line through our points. Like so. And then in order to obtain the acceleration, as always, we just calculate the slope of that line. So the slope of the line is now going to equal the acceleration, and it'll be in terms of meters per second squared. There's a space within the laboratory handouts for you to provide your calculation of the slope. Once again, the slope of this line is the acceleration in terms of meters per second squared. That's basically the first part of this laboratory exercise. The second part of this laboratory exercise is now to calculate the net work and also to calculate the kinetic energy. This will be done in the second data table, but before we obtain that, we have to calculate the net force. So let me do a little bit of erasing here. And then specifically, if we refer to step number 11 in the laboratory handouts, this is where you then provide your calculation of the net force. The net force, of course, is just equal to ma. So you take the mass of the cart, which is 0.06 kilograms, and you then multiply that by the slope of your line from this first graph, the acceleration in terms of meters per second squared. When you do calculate the net force here, keep in mind that force is in terms of newtons. So you make this calculation in step number 11. And now take a look at the second data table that is in the laboratory packet, in the laboratory handouts. That second data table has 3 columns associated with it. Okay, first of all, we have dot number once again. terms of n, 0, 1, 2, 3, 4, and so on, up to dot 9. And then we have the next column, which is the net work in terms of joules. And here's then how you calculate the net work. The net work for the nth dot is going to equal the net force, ma, and then multiplied by the position, x, at the nth dot that you already have measured out from the first data table. So you simply take the net force that you had calculated in step number 11, and then multiply it by the positions that you measured. Note for dot 0, however, that the position is equal to 0, so then therefore the net work done for dot 0 is of course just 0. And then you complete this process for dots 1 through 8. Don't bother to do this, however, for dot 9, because we can't calculate a kinetic energy at dot 9 anyway. That is, by the way, the next column in this data table is the kinetic energy at the nth dot. That's in terms of joules. So the way you calculate the kinetic energy at the nth dot is as follows. You take 1/2 times the mass of the cart and then multiplied by the velocities that you had calculated in the earlier data table, squared. That then gets tabulated here. Once again for dot 0, however, because the velocity at dot 0 is equal to 0, the kinetic energy at dot 0 is equal to 0. And then you just simply make this calculation for dots 1 through 8. Once again, we don't calculate this for dot 9 because we don't have the velocity at dot 9 anyway. By the way, when you calculate the net work done in the second column and the kinetic energy here in the third column, the numbers that you calculate in terms of joules are going to be quite small. Don't round them off. Go ahead and write out all of the digits that you obtain in your calculator when you calculate the net work and you calculate the kinetic energy. And now we get to the last couple of steps of the analysis of this laboratory exercise. What we now do is we then plot these two columns against each other in the second graph. So now take a look at the second graph. On the vertical axis is the net work in terms of joules, and on the horizontal axis is the kinetic energy at the nth dot in terms of joules. So based upon what we calculate here and here, it's going to be up to you to figure out how to scale your vertical axis and horizontal axis. Ideally, you want to scale both the vertical and horizontal axes exactly the same way. Once you've figured out how to do so, you then go ahead and plot your positions of the net work and the kinetic energy. You plot that data here on this graph. And then if you do this, you will then ultimately obtain something that is linear. Like so. Once again, we'll go ahead and draw a best fit line through the points. And now we'll calculate the slope of that line. In theory, because these two columns should be equal to each other, in theory, this then means that the slope of this line should be equal to 1. That slope, by the way, has no units. The reason for that is because the rise and the run are both in terms of joules. Rise over run, those joules will cancel each other out, and you're left with a dimensionless quantity. But in theory, the slope of this line should be equal to 1. Of course, because of experimental errors that I'll describe in just a few minutes, of course, your slope may not be exactly equal to 1. So then therefore, in order to know whether or not you obtained a good result, the last step, and there are spaces provided for you in the handout in order to do this, the last steps now is to just go ahead and calculate a percent error. So the percent error that you'll calculate is going to be the absolute value of the difference between your slope and what it should be, which is 1, and then divide by what the slope should be, which is 1. You'll obtain a decimal. You then multiply by 100 in order to convert to a percentage. Okay, as is always the case when it comes to these laboratory exercises involving spark timers, one of the main sources of error, of course, is friction. And then secondly, keep in mind that we are always assuming that the velocity of the cart at dot 0 is equal to 0. That's not necessarily the case. Remember that the cart is already moving when we start keeping track of it, even though we are trying to move towards the beginning of the tape as closely as possible. So then therefore, the object does have a little bit of kinetic energy at dot 0 already. When we start keeping track of it, that is unavoidable as a source of error. Okay, that concludes this short lecture here describing the analysis of the data for the mini lab exercise called the work energy theorem.